Students, today we are going to introduce the key concept in routing technology, the routing table. In the previous lessons, we learned about the hardware and software of routers and became familiar with the basic concepts of routing. Now, in the routing module, an essential knowledge point is the routing table. First, let's understand what a routing table is. The routing table, also known as the path table, is used to store relevant data, in other words, routing information. It is used for data forwarding and route selection. The routing table contains information such as subnet flags, the number of routers on the network, and the names of the next routers. An analogy to real-life navigation systems, the routing table is like a navigation system on a map. It tells us how to get from point A to point B. Similarly, the routing table stores a table of how paths should be taken. The following image is a routing table on a Huawei router, which can be viewed using the Display Routing Table command in the command line interface. It's essential to note that different router products from different companies may have slightly different routing table formats. But the differences are not significant. Next, let's take a look at the meanings of various parameters in the routing table. The following diagram is an example of a routing table using Cisco routers, and it represents a typical format for routing information entries. The first letter represents the routing protocol code, where O stands for OSPF, R stands for RIP, C stands for directly connected routes, etc. The second segment of IP address and subnet mask represents the destination network address range for IP data packets. The third segment, such as 110.2, represents the administrative distance and metric value of the routing protocol. The address after VIA is the provider of this routing information, and the time afterward is the update time of this routing information. The last port number indicates from which interface the data packet should be sent to reach the destination network. The routing table should be carefully managed to avoid errors, especially when network administrators manually configure static routes. If there are errors in the routing table of some routers in the network, it may lead to routing loops. A routing loop refers to a situation where a packet is sent out from a router, goes through several forwarding steps, and then returns to the initial router. When a routing loop occurs, packets will circulate between several routers until the TTL value becomes 0, at which point the packets are discarded. This results in a significant waste of network resources and should be avoided as much as possible. The topology in the diagram is an example of a routing loop. Suppose the host with IP address 192.168.0.1 wants to send data to the 192.168.1.0 network. If there are errors in the routing tables of routers R1, R2, and R3, what will happen in practice? Firstly, the data is sent to router R1. Since R1's routing table is incorrect, it forwards the data to R2. However, R2 also doesn't know the correct path, so it forwards the data to R3. Similarly, R3 forwards the data back to R1. This creates a data loop, and the data packets never reach the intended destination, the 192.168.1.0 network. This results in severe data transmission errors. As seen, the routing table plays a crucial role in path selection. In order to find the best path and determine the relationship between the destination network and the next hop, routers employ a specific routing selection algorithm. They collect different information and fill the routing table accordingly, ensuring that it accurately reflects the changes in the network topology. Based on the metrics, routers then decide on the optimal path. This process is known as a routing protocol. Routing protocols can be categorized as static and dynamic. Common dynamic routing protocols include IPv1, IPv2, OSPF, EIGRP, IRMP, BGP, BGP4, and others. The principles for route selection are as follows. The longest prefix matching principle takes precedence. They are selected based on the routing protocol's priority. The route with the lowest cost value is chosen. For the same route, packets will prefer the path with the smaller cost value. Different routing protocols have different priorities, also known as administrative distances. When a route is learned from multiple routing protocols, the one with the highest priority will be preferred for use. The priority for the same routing protocol may vary on devices from different manufacturers, but they generally remain consistent. The table below shows the administrative distances for various routing protocols. For example, for the OSPF routing protocol on Huawei routers, its administrative distance, also known as the route priority, is 10. While on Cisco routers, its administrative distance is 110. Route cost refers to the total cost of traversing all the links from the source to the destination. Different routing protocols use different methods to calculate route costs. For the RIP protocol, the cost is calculated based on the number of hops, which is the number of routers in the path. The maximum cost for RIP is 15 hops. For the OSPF protocol, the cost is calculated using the formula 108 BW, where BW represents the bandwidth of the route's entry point. Let's consider an example with the topology shown in the diagram, where each router has a value representing the cost. When router A wants to reach router B, there are two possible paths. Path 1, cost 2 plus 2 plus 2 plus 3 is equal to 9. Path 2, cost 3 plus 3 plus 3 plus 3 is equal to 12. In the end, the data flow from A to B follows the path with the lower cost. Equal cost multipath, ECMP, refers to the existence of multiple paths with the same cost to reach the same destination address. ECMP allows for load balancing, distributing traffic across multiple paths, and also provides route redundancy and backup. In the example, with the topology shown in the diagram, where each router has a value representing the cost, there are two paths from router A to router B. Router A calculates the cost to reach the destination address B and finds that both paths have the same cost value, making them equal cost routes. When forwarding packets, router A can choose to distribute the packets across these two paths. Now, please complete the following assignments. The above is the content of our class today. Everyone should review the content of this lesson carefully after class. In the next class, we will conduct experiments on configuring static routers. See you in the next class.